All right, so here's number 4 in test 1, the free response. Let's go through this problem right here. Okay, the first part, it says you're given that table for f prime, g, and g prime, and you're defining h to be f of g of x minus g of f of x. It says explain why there must be a value c on the open interval from 1 to 4 such that h prime of c equals 0. This looks like a mean value or specifically a Rolls idea here. So going through this, if I take h of x equal to f of g of x minus g of f of x, if I take the derivative of this function, I'm going to get f prime of g of x times g prime of x minus g prime of f of x times f prime of x. Okay? Now, we're told that somewhere on this interval, h prime at c equals 0. All right? I need to show this. Well, again, since my interval's on the interval from 1 to 4, right? And it says the functions f and g are differentiable everywhere, therefore h must be differentiable everywhere. So I need to find h at 1 and h at 4. Well, h at 1 says that's going to be f at g at 1 minus g of f at 1, and the same thing goes for 4. You can do the compositions on your own. Okay, I've just done the compositions, and I got h at 1 to be 0, and I got h at 4 to be 0. So now, applying these numbers into AROC, I would get h at 4 minus h at 1 over 4 minus 1, which would give me 0 minus 0 over 3, which is 0. Well, again, since this function is differentiable, since f and g are differentiable everywhere, h is differentiable everywhere, and that means that it must be differentiable and continuous on the closed interval 1 to 4 and on the open interval from 1 to 4 respectively, and therefore I know that there must be some value where h prime at c is equal to 0 by the mean value theorem, or more specifically, you can also say Rolls. Okay, part B says if h prime at 3 equals 0, then find the value of g prime at 3. Find the derivative of g at x equals 3, right? Again, I've already set up the derivative here. So basically what I need to do on this, again, since f and g are differentiable everywhere, then they're continuous everywhere, and therefore h is as well, right? Well, at this point, I know that I can put 0 in for h prime at 3. And wherever I see an x, I can replace that with a 3. All right, now, looking at my table, I can see that g at 3 is 5, and f prime at 5 is 8. G prime at 3 is called k. F at 3 now, looking at this, f at 3 is 1, and g prime at 1 is 9. And f prime at 3 is 5. And so basically I get 8k minus 45 is equal to 0. So wouldn't k equal 45 over 8? And that's part B. Okay, part C is a fun little question. It says, let W be defined by the function W of x equals 7 plus the integral from 1 to f of x of g of t dt. Write an equation on the line tangent to W at x equals 3. So the first thing I got to know, I know I need a point on my graph, and I need the slope of my tangent line, right? And the point's going to be 3, comma. Well, again, to find the y value, I've got to find W at 3. Which says find 3 or 7 plus the integral from 1 to f at 3 of g of t dt. Now, if I look at f at 3 on my table, f at 3 is 1. So w of 3 equals 7 plus the integral from 1 to, oh golly, f at 3 again is 1 of g of t dt. And since the upper and lower limits of integration match, I know that's 0. So it'll just be 7 plus 0, which is 7. So I now know the point that's on my tangent line. It's 3, 7. Now I got to find the slope, right? Well, to find the slope, I need to take w of x, which equals 7 plus the integral from 1 to f of x of, of g of t dt. And I need to take the derivative of both sides. Now the derivative of 7 is just 0. Plus the derivative of this guy with respect to x, well, that's the fundamental thermocalculus part 2, which would just be g of f of x times the derivative of that inner composition of f prime of x. So now the derivative at 3 would equal, well, the 0 cancels out, g of f at 3 times f prime at 3. So that gives me the derivative of 3 would equal, well, f at 3 is 1, and g at 1 is 2 times f prime at 3 is 5. So that's 10. So my tangent line would just be y minus 7 equals 10 parentheses x minus 3. And that's question 4 in test 1. Bye, guys.